All right. Everybody. Thanks for coming to the latest now in series of lunchtime seminars. Apologies for the slight delay, the room a little bit later than usual. Today we have Hubert Owusu, an application engineer at Polytech, specialising in vibrometers, which this is one. With over a year of experience in the field, Hubert has a deep understanding of vibration measurement technologies and its application across various industries. At Polytech, he provides technical expertise and support to customers, helping them optimize their measurement processes and achieve their goals efficiently. Hubert holds a bachelor and honours degree in mechanical engineering at Coventry University and enjoys playing drums and cycling. Without further ado, over to you, Hubert.
Thank you, Mark. Hi, everyone. Thank you for having me today. So my presentation is going to be mainly on 3 points within 30 minutes. And then I will have 15 minutes of questions and answers. So I will gently ask if you have had questions, maybe send it through my email and then I'll come back to you. So today is just easy questions. All right. Okay. So I will start by introducing Polytech. Who are we, what we do, where we fit in, and what we do as a whole company. We are a global company and our HQ is in Germany, Waldbrunn. Near to the Black Forest. So if you guys know where the Black Forest towards the Cashrow area, so that's where we are situated. Yes. So what do we do as a company, and what do we fit? Where do we fit in? To be honest, I was discussing this with Mark earlier. So for us, you can see, you can touch, you can feel, you can hear. We can't measure. That's sort of things we do. So we are sort of pioneer of vibrometers and scanning laser vibrometry. We do accelerometry as well. So also surface metrology. For example, if you want to measure RA or surface roughness, depth, cracks, that sort of things. Surface metrology is what we do that as well. Of course, we do also process analytics. We do machine visions and optical system. So what area do we fit in? We fit in all areas because everything moves and everything requires sort of instrumentation to be measured accordingly. But our biggest sort of customers are mostly academics, automotive companies, acoustic engineers, but also we have a strong footprint in medicine. We have also strong footprint in insect studies as well. And currently we are also learning food and agriculture. And I was discussing with the Mark an application we had a couple of years back on Grapefield where some insects were sort of disturbing, but yes, we use some of our equipment just to do that. So now let's get to the fun bit, vibrometry. So we use laser, we use Doppler effect to measure to measure. So Doppler effect, we all know what Doppler effect is. So our vibrometers, we measure out plane measurement. So in this direction, Z direction. Why do you need a vibrometer, or why do we need to measure vibration? After all, why is it important for engineers, for acoustics, for medical people? Why do we need to measure that? Because sometimes there is unpleasant sounds that we don't want as engineers, and sometimes there is a pleasant sounds that we want as engineers. Therefore, there is a need for an engineer to, of course, have instrumentation or an instrument to quantify that sort of frequency or measurement. And also, what do we need to measure vibrations? Of course, we use it as a benchmark to do pass or fail on materials, just to understand its failures or fractures or wear or cracks. So it's also important to, of course, do that analysis as well as, of course, as indicator for product quality, which we have some products where we use it for pass and fails, which is called IVS, and it's mainly for industrial purposes. Now let's look a little bit the benefit of using vibrometers. It is contactless. What does that mean? It means we use a laser light to shine on the specimen or on the device that you are interested to measure, which means you don't have any you don't have any influence on the object, and it's very accurate and precise. Another benefit, no mass loading. Of course, it depends the specimen. Of course, if you're measuring a bridge, using a conventional accelerometers or the conventional instrumentation out there won't make any difference. But if you're measuring a MEMS, of course, that make a huge difference on the instrumentation that you use. Again, many points can be measured by using vibrometers compared to the conventional instrumentation out there. You could measure about infinity amount of points. Reaching the difficult places where again, the conventional instrumentation, sometimes you may struggle. For example, if you want to go through maybe a piston where you cannot physically attach a accelerometer on top of it whilst it is operating. Therefore, it is really important to sort of have equipment or a tool where it could assist you in that sort of area measure. And also for measuring on a soft, thin, joint, and hard surfaces, which is really important when it comes to in the industry, especially in the manufacturing industry, for maybe mailing and that sort of things. You don't want physically to be touching or to moving. You want something just line of sight, point and shoot and measure. And large working distance. So today I have with me a vibro which has capability to go up to 20 meters, but with our longer range can go up to 300 meters from point and shoot. So far as you have a clear line of sight, you can point and shoot and measure your object. And of course, we have overcome the drawback from contacted transducers, which was an issue in the industry. So Polytech with our laser vibrometer contactless, this has become a bigger solution for people in that industry. So now let's look at how to capture a measurement. What do we capture? What are the units we can go up to? So we can capture anything from small to large, from B antenna to Elizabeth Tower. You just name it. We can measure from microns to meters. From slow to fast, anywhere from millimeter per hour to 100 kilometers per hour, that sort of things. We measure small to large amplitude, anything from picometers to meter spectrum as for in displacement. So it has a deeper capability to reach the amplitude if you require. And as well as slow to high frequency. So one thing about our instrument is it go up to DC, which means the zero, we can measure from 0 hertz to upwards. So there is no limitation when you want to capture within something in the lower frequencies, which sometimes is really challenging for your traditional conventional instrumentation out there. And now let's look at how our vibrometer works. So this is our PSV 500. And what we do, we shine a laser light out and goes to the wall. So you have a speckle light. And within the speckle light, we receive some light back. So the light will go through some detectors and then it will come out. Then we will have a digital information where we will be able to read and analyze it. But as well as digital, we can also acquire data analogically by just plugging it through BNC to your DAC system, just to also analyze the data, raw data from the vibrometer. So now this is a little bit of on our portfolio, some instruments that we have. So we have 2 types of equipment on our portfolio mainly. And the first categories are the single point. And as you can see, this is one of the single point vibro portable. What does single point mean? Single point is just one laser light from the sensor. And if you want to do multiple measurement, that means you need to physically move the laser to the specimen or the object you want to measure. So this is one of our single point vibrometer. And also we have the modular vibroflex. What does that mean? We have just a single mother head, which is the connect box, this big box over there, and then we have many heads which can be connected to the VibroFlex Connect to measure whatever you want to measure based on the application. For example, if you have an application which you need to go through liquids, we have a separate sensor head which could do that. Or you want to measure maybe a difficult surface, engineered surface, rough surface, door surface, dark surface. We have a separate head that do that. And then this was our long range measurement unit, which we have, it go up to 300 plus meters. It could capture that. And the IFV is our industrial vibrometer. We use it for pass and fail mainly, where most engineers like using it because it just makes their life easier. They have already set it, so you just say this is good and you get to go. And we have our compact, which is for small items such as capacitors or on your PCB board. And we have our high speed, and this is mainly used in the automotive sector. So now let's look at this one, the scanning system. So the scanning system, from difference from the single point, from the scanning system, you can measure many points just from one sensor. So the way it does it, it has a mirror in the sensor head, which could move the laser light based on the position and the grade you have already set to measure. And within this scanning portfolio, we have three mainly. We have the 1D, we have the 3D, and we have the RoboVib. So the 1D, of course, means we have just one head, which measure just out of plane movement, only Z direction. With the 3D, we capture out of plane movement as well as the in-plane movement as well, because of the three heads. It could capture that trigonometry, that sort of things. And we have the RoboVib if you have a larger object which you want to measure, like you see from the picture, the RoboVib does that correctly. But we also understand that sometimes special inquiry come through, which requires special instrumentation. So we have also a single point which could also measure just in plane motion. So if your measurement, you want a single point, you don't want a scanning system, and maybe a scanning system is not right for you, we have IPV, which measure the in-plane motion for you to capture that. And also we know that sometimes you need to measure your differentials. We have the differential laser vibrometer fiber, which measure your differentials for you. And we have the RLV, which measure torsion, rotation, that surface, and mostly is used in the automotive sector for shafts, that sort of things. We have these ones is especially for MEMS applications, is two things in one. So one, you have your PSV system in a single point MEMS application where you could measure your MEMS as well as seeing the operational deflection shapes, how they move and that sort of thing. So we have the MSA 600 and MSA 100 3D, which go all the way up to the 2.5 gigahertz, so enough to capture the frequency you are sort of interested in it. So now let's talk a little bit about applications. What do we do? What do we measure? And I've prepared something about the break days, and I also did a measurement on a break days, which I will show later on how we use our software to do that. Why is it important after all? Because we have already understand that noise can be good and can be bad, and depending on which noise you perceive can be pleasant or not unpleasant, and therefore it's important for engineers to understand and therefore work around that sort of things. So it's important to sort of understand what the clients are saying and therefore work on your specimen or on your objects that you want to measure. So with that, we could use also our system and use in FEA modulation to have a predict high, not linear system, and therefore it's good validation to help you to limit the model uncertainty. So this one thing that we do as well, we use our scanning system just to do measurement on a brake disc or to measure whatever you want to measure. But today, brake disc is what I was going to show you. I'm going to show you a measurement that I did in the office prior coming in. There you go. Okay. So this was a 1D scanning brake disc I did in the office, and it was about 600 plus points on this brake disc. So with your traditional modal hammer tap measurement, will take you forever to do 600 points. But with this, approximately took me around 3 minutes just to do a single scan on this, and it go up to 10 kilohertz of bandwidth, that sort of spectra. But the reason why I want to show you this is upon so upon measuring your specimen, or the brake disc in this case, you have a spectra. So this is your operational deflection shape data, and this is not your model analysis. And therefore, it's really important to have this, which sometimes you just use a vibrometer to do this, but this one works. It works your angles for you. The computer calculates your angles for you, so you don't need to calculate your Z, your Y, and your Z coordinates. It work out the distance, how far maybe the sensor head was from to the brake disc. It worked that one out for you, and already you have an idea how the brake disc is behaving. But not just that, you could also take it to the you could take it to yes. You could take it to our post-processing to analyze the brake disc. So what is happening over here, I've already obtained my ODF and I want to analyze the brake. So that's where the fun bit happens. So here you get to analyze your MAC value, your Modal Assurance Criterion. You get to analyze your FRFs on around the 600 points, which I define. And here you could tell the system that analyze about 10 points, which I've already preset. And the system is calculating it for you and is showing you which are your model shapes. And upon seeing your model shapes, then you can compare your model shape to the ODF to see whether it actually correlates to your analytical, which as you have already calculated. So this is one of the tools I tend to use mainly for the automotive company, because they like this polywave software, which helps you because it's still measuring. Once it's done, I'll be able to show you some data. Here we go. Okay, so now I could see I have about 10 frequencies over there, but only only 5 of them is showing out to me, which means there is something going on at 110.9, which I'm not happy about. So what the system help you to do is find a spot which you're not happy. In this case, it's this spot that is highlighting that there was something going on this spot, which I'm not really interested in, or there's something which I need to closely look at it and maybe make a modification from maybe manufacturing, or maybe whilst I was just doing the measurement, that bit maybe it's not grade properly or it's not fine properly, that sort of thing. So these two sort of give you an understanding of a overall view of what is happening to the brake disc. Just show you what is happening to the brake disc, and as well as you could see the Mach value if it's where you want to be, and check if there is a similarity, because what tends to happen on brake disc is because it's a circular, you tend to have similar deflection shape at different frequencies, which in the automotive sector is really important for them to capture that values, and therefore they could work on maybe harmonics happening over there, or there's something which they are not quite interested in and they want to sort of make the modification. But I wanted to show you this just to show you the importance of having an ODS, operational deflection shapes, and taking that raw data to your model analysis. And when I was in uni, I used MATLAB to do that process, which is a little bit lengthy because you need to build your own code. And if you get maybe even a dot or a comma wrong, it just drives you crazy, and it doesn't tell you where you're even getting that wrong. But what this software does is just work everything at the background and show you directly where you need to sort of make changes, as well as you have your FRFs, where you could see all the FRFs over here if you select them. But going back to the presentation, there we go. There we go. Yeah, so going back to the presentation, now we know some importance of what we're doing it. But again, I want to show you tires, why we measure tires as well, which has become a huge topic nowadays for EV cars, which I believe Tesla is using foams to put in their tires just to reduce the noise on the road, because just two things happen when you're driving a diesel or petrol car. Once you go over 40 miles per hour, all you hear is your tires and the wind. And yeah, so with EV cars, it's a huge topic now, and engineers are working tirelessly to understand where or what they need to do just to minimize this unpleasant sort of noise in tires. Touch on the Mach value. Yeah, I want to show you MEMS device. So MEMS device, we do measurement device from pressure sensor. And if you have telephones, once upon a time, it has gone through one of our machines just to do a check, benchmark check on it. So pressure sensors, micro mirrors or RF MEMS, that sort of things. We do measure all these instrument which before it was almost impossible to measure. But whilst I'm here, I will also show you the vibro goals as conditioning monitoring. So we use our vibrometers to also do a conditioning monitoring, and it's really important for engineers to do a conditioning monitoring. And vibro is one of my favorite instruments where you could remotely set it to do conditioning monitoring without you being present, because it has a Wi-Fi capability where you don't physically need to be next to the object. So you could connect it wirelessly and move away from it and set it, and it will measure the data for you. So here you could see a little bit spec about the vibro, which I already have it over here. So it is remote control. It has power capability, battery powered capability. Has outdoor proof, which rates about IP64. In the rain, of course, I do not advise to put it to your pool or something like that. But of course, if it's raining, you could take measurement with the vibro. And as well as I said, for the instrument, for the biometrology is really a big sector now, where frequencies and, you know, understanding chips of insects, crickets, that sort of things. There is a big studies on that sort of thing, insects and crickets, where it's going on, and they're all using vibrometer just to understand what's going on. But just to say, just to conclude, I believe there is a huge and a bigger market and a bigger something out there where perhaps maybe engineers or yourself haven't yet touched it. But what I want to say, so for us, you can see it, you can touch it, you can hear it. We are there to assist you in all your applications and your endeavors. Thank you very much for having me today. If you have any questions, please do. The easy ones, of course. And the hard ones, you could send it to my email and I'll get back to you.
Do you have any questions in the room for Hubert? Oh, yeah.
Well, I'm interested in the robotic one that you had up earlier when you were showing the different models. I'm just curious, is that like an all-in-one system where you get the arm and everything else, or is it a modular thing that fits into, say, another company's sort of robotic arm, and you just attach the vibrometer, that makes a Doppler vibrometer back?
Yes, right. So the arm itself is a third party. It's not one of our IPs. So we buy it from somewhere and attach it. So of course, so for us, you could maybe get a better deal on the market by all means. But of course, we can also supply you that as well.
Well, because we have a robotic center here
Right.
with the arms already there.
Yeah.
So it's kind of curious that you selves have like you would want to attachment, but I'm just curious whether it was only one thing, whether we can have that and then bring it to them and then hopefully.
No. The heads are separate. That is one of the PSV heads. So you just attach the PSV heads. Okay, try to go on that last slide, but it looks like it's not going over there.
But it's anything, it's a modular thing that will connect to our value number.
Yeah. So what we did is these three attached to that's surface and maybe longer cables. Yeah.
Now I've choked. I was just wondering about the 3D system and how the heads align with one another, because on the robo bit, it's obviously attached to its own bracket, so you know where they are, but the way to be pictured there, I'll really take the drive off. So I was just wondering how it works out, what the relative position is.
Yeah, so that's really good question. So we set the arm as equilateral triangle at the beginning. But within the software, we have something called 2D and 3D alignment, where you teach the sensor head and the mirrors where you want to position the laser that is coming out. So you teach the laser where you want in a bigger spectrum, and then the system just work out for you the trigonometry and your X, Y, Z angles, that sort of thing. Yeah.
Okay. So on the 1D system, you have a process where you line the layers and things. You just go through that with all three heads and it works out their interrelation as well.
Yeah, so the difference between the 1D and the 3D is the 1D just measure out of plane, so it works as single point. So it's just perpendicular zero angle,
Yep.
Point and shoot. But the difference is you set your 2D alignment grid on perpendicularity at zero angle. So for example, if I was just measuring the beam, I'll make sure that my tripod is straight, the head is straight. And if the head is not straight because the object is down, I need to account for that angle and then work it out later on. So, and the difference from the 3D is the 3D, you don't need to account how much because of it has 3D heads, and it measure also the output plane and also take account that we call it cosine error, take account the cosine error and work it at the background for you. Whilst the 1D doesn't, you need to physically do the calculation yourself. I mean, we rent them as well, so.
So any other questions in the room? Okay. Just curious about the fact that, mentioned like, the normal to the surface that you want to, take a measurement of, and that's fine for flat surfaces, but the curved surfaces, or proper, that's some, maybe, you have a curve something, many tangents you can take a recording of what's, how your systems be able to.
All right. So there was this study, now I forgot about the study, and they use, just trying to remember the name, they use this probe, I forgot the name of the probe, but they use that probe which measure from DC, from 0 to upwards, and we use also our vibrometer. What we don't take account, we don't take the surface movement of the object. So we measure from where it points at it. So even if your object is maybe curved that way, wherever we point at, that's what we are getting. So it's not a matter of how much your surface is curved or is bent or so forth. So for us, we can point the laser on it, receive light back to the sensor head, good to go. Yeah. So it doesn't matter the surface.
Okay.
Yeah, the surface doesn't matter. Of course, we have, I mean, if your surface is door, we have special vibrometer for that. If is your surface is biological surface, maybe flesh or something like that, we have a different vibrometer for that. So you can use just one vibrometer for all applications. So based on application, change vibrometer that you want to use. That sort of thing.
Any further questions? I don't think we've had any online, so I'll just like to thank you again for when you're here building on top.
Thank you. Yeah, thank everyone online.
See everybody again next week. That's it.
Thank you.